Let's talk about what it means for two polygons to be similar. We learned in first semester that congruent polygons have all pairs of corresponding angles are congruent and all pairs of corresponding sides are also congruent. And what we're learning today about similar polygons is similar, no pun intended, but instead of the sides being congruent to each other, the sides will be proportional. So two polygons will be similar if all of their pairs of corresponding angles are congruent and all of their pairs of corresponding sides are proportional. Remember that proportional means that if you write their side lengths as a ratio and then reduced that ratio completely, all of the ratios that represent corresponding sides of each polygon would reduce to the same thing. They would be equivalent fractions. We can write similarity statements in a very similar fashion to how we wrote congruent statements in first semester. You write the name of each triangle, or whatever kind of polygon you're given, with this symbol in between. This single squiggle means similar. So this would be triangle ABC is similar to triangle XYZ. Since the sides are proportional, that means we can calculate something called a scale factor. The scale factor of two similar polygons is the completely reduced version of the ratios of their side lengths. And we can calculate the scale factor by setting up a statement of proportionality. A statement of proportionality is a set of ratios that compare corresponding sides of each triangle. So you can use this statement of proportionality to identify that side AB corresponds to side XY. These two sides correspond. And that BC corresponds to YZ, and that AC corresponds to XZ. So let's give it a try. We're going to use this similarity statement to answer these questions. Looking at these two similar triangles, which angles are congruent, and which sides are corresponding. Write that as a statement of proportionality. All of the information that you need is located in the similarity statement, because the order of the letters in each triangle's name corresponds. So the first letter in the first triangle's name is an L, and the first letter in the second triangle's name is a P. That means those two angles correspond, so they're the first pair of congruent angles. Angle L is congruent to angle P. M is the middle letter and Q is the middle letter, so those two angles must be congruent as well. Angle M is congruent to angle Q. And N and R must also be corresponding angles, and therefore they are congruent because the triangles were similar. So you can identify which angles are corresponding and therefore are congruent by looking at the similarity statement. We can also use the similarity statement to write the statement of proportionality. Instead of just looking at one letter at a time, which would represent an angle, we're going to look at pairs of letters, because that would create a segment. So for example, LM are the first two letters of the first triangle's name. That's this side right here, side LM. That side corresponds to PQ, because those are the first two letters of the second triangle's name. So these two sides correspond, and I'll write them as a ratio. And I'll set that equal to my next pair of corresponding sides, which again I can find by looking at my similarity statement. M and N are the last two letters of the first triangle's name, and Q and R are the last two letters of the second triangle's name, which means those two sides must correspond as well. So I'll write a second ratio comparing those two sides. It is important that you write your ratios in the same order. If you write the side lengths of the first triangle, triangle LMN, on top first, and PQR's side lengths on the bottom, you need to be consistent across that all the way across the statement of proportionality. Finally, we have the first letter and the last letter, L and N. That would correspond to the first letter and last letter in the second triangle's name, so these two sides are corresponding as well, and I'll write a ratio for those to complete my statement of proportionality. Okay, for our next example, we're supposed to figure out whether or not these two triangles are similar. Well, remember that the definition for similarity is that they have to have all of their pairs of corresponding angles are congruent, which we can see that in the diagram. All of our pairs of angles are congruent, so that half is good to go. But the other half of the definition is that all of the pairs of corresponding sides must be proportional. And that's not really something that you can tell just by looking at the diagram real quick. You're going to have to do some math. To get started, I'm going to write a statement of proportionality. This time I don't have a similarity statement to work from. obviously, because I don't know that these triangles are similar yet, so of course I can't have a similarity statement. So to set up my statement of proportionality, I instead need to look at the side lengths that I've been given. You can basically categorize them as small, medium, and large. The smallest side in one triangle must correspond to the smallest side of the other, and medium to medium and large to large. If you didn't have side lengths provided to you, another way to set up your statement of proportionality is just by looking at which sides connect which angles. ST, for example, connects the angle with one arc to the angle with two arcs. And so does VW. It connects the angle with one arc to the angle with two arcs. So if you don't have side lengths to be working from, then instead you can look at what kind of angles are connected by each side and set up your statement of proportionality that way. But since we have side lengths labeled on all of our sides, that's the easiest way to go. So I have short side over short side equals long side over long side equals medium side over medium side. So this is my statement of proportionality, and then I can plug in all of my numbers based on what I see in my diagram. And the next step is to simplify each of these ratios. And we're hoping to get the same fraction each time when I reduce. Because if I do, if all three of these fractions reduce to the same thing, that means the triangles must be similar, because the side lengths were proportional, and because, as we said earlier, each pair of corresponding angles were congruent. So let's reduce. 12 and 8 are both divisible by 4, so that reduces to 3 halves. 10 and 15 are both divisible by 5, so that also reduces to 3 halves. And 18 and 12 are divisible by 6, which means that also reduces to 3 halves. Therefore, these two triangles must be similar because all of their pairs of corresponding angles are congruent, and as we just proved, all of their pairs of corresponding sides are proportional. So now we can write a similarity statement to describe how these two triangles are corresponding to each other. If I call the first triangle STU, for example, you can call it TUS or UTS or whatever you want to call it. I'm going to call it STU. I have to write the letters that represent the vertices of the second triangle's name in a corresponding order. So if I go from the 1 arc angle to the 2 arc angle to the 3 arc angle for my first triangle's name, I need to do the same order when I name the second triangle. So I'm going to say that triangle STU is similar to, remember that's a single squiggle, triangle VWX. This is not the only correct similarity statement. There would actually be 6 correct ways to write these letters. As long as you're writing them in a corresponding order, it's correct. The statement of proportionality we actually wrote on the previous slide, as well as the scale factor, so that completes this problem. Next up, we're going to solve for missing angle measures based on the fact that these two triangles are similar. So basically we see that triangle big is similar to triangle small, and we need to use the information that we've been provided both on the diagram, and remember the order of the letters in our similarity statement tells us a lot. We're going to use that information to solve for angle I, angle G, angle M, and angle S. Well, let's see. I see that angle B is 83 degrees. B is the first letter in the first triangle's name. S is the first letter in the second triangle's name, so that means that those two angles correspond, and since they're similar triangles, they must be congruent angles. So angle S would have to be 83 degrees as well, because angle B was 83 degrees. Well, what can we do with this 54? That's the other angle measurement that we've been given. 54 is the measure of angle L. L is the last letter in the second triangle's name, and G is the last letter in the first triangle's name. So that means that those two angles are corresponding and therefore congruent. So angle G must measure 54 degrees. But how am I supposed to figure out angle I and angle M? They're corresponding because they're the middle letter out of both triangles' names, but I don't know either of their angle measurements. But remember from first semester that the sum of the interior angles of a triangle is always equal to 180 degrees. So I could write something like this. The measure of angle B plus the measure of angle I plus the measure of angle G equals 180 degrees. And then I can substitute in the numbers that I know. I was given on the diagram that angle B is 83 degrees, and we figured out that angle G must have been 54, so the only thing I don't know is angle I. To solve, I can subtract 83 and 54 from both sides, and I find out that the measure of angle I is 43 degrees. And if I measures 43 degrees, then angle M must measure 43 degrees as well. In our next example, we're going to solve for some missing side lengths instead of angle measures. Given that these two triangles are similar to each other, that triangle JKL is similar to triangle PQR, we can solve for x by setting up a proportion. 60 and x, those are corresponding sides, so I can write that as the first half of my proportion. And I'll set that equal to another ratio that represents corresponding side lengths in these two triangles. But I need to be sure to use a ratio that's complete, that I know both parts of. In other words, I don't want to use side QR for this because I don't know how long QR is. All I know is that it's 7y plus 6 centimeters. So instead, I want to use PR, and PR corresponds to JL. So I'm going to use 80 over 100 for the second half of my proportion. Then I can cross multiply and solve. So x must be 75 centimeters. Let's do something similar to solve for y. I'll write 100 over 7y plus 6 because KL and QR are corresponding. And I'll set that equal to, well, no need to reinvent the wheel. I can just use 80 over 100 again. It worked last time, it'll work this time as well. So let's cross multiply. Don't forget to distribute. We talked about that in the previous lesson, that if you're multiplying 7y plus 6 times 80, you have to multiply both parts of this by 80. So it's 7y times 80, that's 560y, and 6 times 80 is 480. And then, of course, 100 times 100 is 10,000. So let's subtract 480 from both sides and divide by 560, and I find out that y must be 17 centimeters. In our next example, we're going to kind of do a little bit of everything. We're going to identify corresponding angles, corresponding sides, scale factors, the whole thing. So let's take a look. Given that quadrilateral ABCD is similar to quadrilateral WXYZ, which of the angles is congruent to angle A? Well, honestly, for something like this, I don't even look at the diagram. The similarity statement tells me everything I need to know. A is the first letter, and W is the first letter, so A and W correspond, and therefore are congruent. Same idea with X. X is the second letter, B is the second letter, so they correspond. It's a lot more reliable, and in my opinion a lot easier, to figure out that kind of information from your similarity statement instead of from your diagram. Especially because not all diagrams are necessarily drawn to scale, it can be very unreliable to look at the diagram and try to determine which angles are congruent to which just by eyeballing it. Instead, get your information from the similarity statement. Now let's try to complete some proportions that are missing a part. My first ratio says AB over CD. Those are the first two letters of the first quadrilateral's name and the last two letters of the first quadrilateral's name. And that's set equal to WX over something. Well, WX is the first two letters of the second triangle's name. That corresponds to the AB that we saw to begin with. So I need to make this question mark correspond to the CD that we saw in the first ratio. Well, CD were the last two letters, so my answer here must be YZ, because those are the last two letters of the second quadrilateral's name. Whenever you're given the question mark in the first ratio, it can feel a little confusing. So instead, look at the second ratio first. BC over DC. BC are the middle two letters of the first quadrilateral's name, and DC are the last two letters of the first quadrilateral's name. So that kind of sets up what we're working with. Then I can compare it to the other incomplete ratio. ZY, yep, those are the last two letters of the second quadrilateral's name. That corresponds to CD or DC that we saw in this ratio. Well, the numerator was the middle two letters, so to complete this ratio, I again must need the middle two letters. So XY would correctly complete this ratio. And last but not least, we have, well, again, the question mark is in the first ratio, so I'll come back to it. I'm going to look at the second ratio first. YX are the middle two letters of the second quadrilateral's name, and CB are also the middle two letters of, but this time, the first quadrilateral's name. So unlike our first two proportions that kept it consistent in each ratio comparing side lengths within the same quadrilateral, our last proportion is comparing the middle two letters of one to the middle two letters of the other. Okay, so let's look at this first ratio again. I have ZW. ZW, those are the first and last letters of the second quadrilateral's name, so I must need the first and last letters of the first quadrilateral's name. So the answer here would be DA. Next up, I want us to calculate the scale factor from quadrilateral ABCD to quadrilateral WXYZ. You'll notice I went ahead and color coordinated everything. I love putting colors on diagrams like this. It really helps me to identify which things correspond to which in a quick fashion. So all I did to do the color coding is I was like, okay, so A and B are the first letters, and W and X are the first letters. So these two sides must correspond, and I'll color them the same color. And then B and C are the middle two, X and Y are the middle two, so I colored BC and XY the same color, and so on. And that really makes setting up our statement of proportionality so much easier. And in order to calculate the scale factor, we're going to have to use a statement of proportionality. So let's do it. AB over WX equals BC over XY equals CD over YZ equals AD over WZ. See how easy it is to set up your statement of proportionality if everything is nicely color-coded according to your similarity statement? It makes things go way faster. So the next step is to plug in all the numbers that we know, because some of these lengths we have a measurement for, but some of them we don't. So let's fill in what we do know. AB is 16, and WX is 24. BC is 12, but I don't know what XY is, so I'll just leave it as XY. And I don't know what CD is, so I'll leave it as CD. YZ is 27, AD is unknown, and WZ is 30. So looking through these four ratios, there's only one that's complete. It's this one. I know both the numerator and the denominator, whereas the other three, I'm missing one of my numbers. So to calculate my scale factor, I'm going to take that ratio and reduce it. So K, which is for whatever reason the letter that we assign for scale factor, I don't know why, there's no K in the phrase scale factor, but K is what we use. K, the scale factor, would be 2/3 if I reduce the fraction 16/24. Now we're going to use that statement of proportionality to help us calculate missing side lengths. Remember, this is the statement that we wrote, and if we're being asked to calculate the length of AD, then I need to pick the ratio that has AD. But in order to solve, I need to set up a proportion, which means I need two ratios. So one of the ratios is obviously AD over 30, because I need to solve for AD. The other ratio has to be the one that you know both parts of, the complete ratio. So I'm going to set 16/24 equal to AD over 30. Then I can cross multiply and solve. So AD must be 20 meters long. So we're going to do something similar to find the length of DC. And you might look through here and say, well, there is no DC. What am I supposed to do? But remember that segments have two names, so DC and CD are the same thing. So I'm going to use this orange ratio and set it equal again to my complete red ratio. And cross multiply and solve. So CD is equal to 18 meters, which means DC is equal to 18 meters. And last but not least, we'll use 12 over XY to solve for XY, setting that equal to our complete ratio of 16 over 24, cross multiply, and solve. I went ahead and labeled my diagram with all of the information that we just calculated about the missing side lengths, and I'm going to use that to calculate the perimeters of each of these quadrilaterals, and then we'll compare. The perimeter of quadrilateral ABCD would just be 16 plus 12 plus 18 plus 20, which is a total of 66 meters. The perimeter of quadrilateral WXYZ would be 24 plus 18 plus 27 plus 30, which is 99. What do you notice about those two perimeters? Specifically, if you set them up as a ratio, how does it compare to our scale factor? The ratio of 66 over 99, that reduces to 2/3, which is the same thing as the scale factor of our side lengths. So that can be a shortcut for calculating a perimeter of a polygon if you have two similar polygons and you know the scale factor between those two polygons. You can use it to figure out the missing perimeter. And also, it's just a handy way to double check your answer if you know both of the perimeters and you know the scale factor. For our final example, we're going to determine which of the triangles on the screen are similar to each other by comparing their corresponding sides. Let's start by comparing triangle FGH and triangle BCD. In order to determine whether or not these triangles are similar, I need to compare each of their corresponding sides and reduce each of those ratios to show that they're equal. If they're not equal, then the triangles aren't similar. The easiest way to do this is to set up a statement of proportionality, and I like to start with these small sides, and set that equal to the medium length sides, and set that equal to the longest sides. You don't have to do it in that order by any means, but I find it keeps me organized by doing small, medium, and then large. Then you'll need to reduce each of these fractions. They're awful big, so you might need a calculator to help you out, but 96 over 48 would reduce to 2 over 1, but 180 over 88 reduces to 45 over 22, and 216 over 100 reduces to 54 over 25. So all of these ratios ended up being different than each other. And in fact, even if only one of the ratios was different than the others, this would still be enough information to say that these two triangles are not similar, because their corresponding sides weren't proportional. Now let's compare triangle FGH to triangle RST. Again, I'm just going to set up a statement of proportionality going small over small equals medium over medium equals large over large. The next step is to reduce each fraction completely. 96 over 64 reduces to 3 over 2. And 180 over 120 reduces to 3 over 2. And also 216 over 144 reduces to 3 over 2. So since all of my corresponding sides reduce to the same ratio in their most simplified form, these two triangles must be similar. So I'm going to write a similarity statement to say that. It is important that you write it so that the letters go in a corresponding order. If I call my first triangle FGH, I have to call the second triangle RST because that goes in a corresponding order. I can tell that because F to G, that connects the smallest side, 96, and then G to H, that's the medium side. So if I start with my smallest side over here, I either go S to R or R to S. I have to go from R to S because that would lead me to my medium length side of S to T. So RST would be the corresponding order of letters compared to FGH. And finally, let's compare triangle FGH to triangle KLM. Small side over small side equals medium side over medium side, which is equal to large side over large side. Let's reduce. I get 4/3 and 4/3 and 4/3. So since all of these ratios reduce to the same number, these two triangles are similar. Again, make sure that you write your letters in a corresponding order. And that's the basics of what you need to know about similar polygons. In our next lesson, we'll do a more in-depth exploration of how to determine whether or not two triangles are similar.